we were basically trying to see how we can solve higher degree polynomials, and as I was mentioning last time that, the higher degree polynomials get a little bit difficult to try and find their solutions to, because you don't have a nice, neat formula like we do with the quadratic formula, to solve a second degree polynomial. So we had just started talking about, with the multiplicity. The idea is if it's a nth degree polynomial, then you should have a maximum of n roots, including multiplicity. So again, if it's a sixth degree polynomial, then technically we should have six solutions to that polynomial. And again, keep in mind, including the multiplicity. We had also talked about the conjugate pair theorem. So the idea here was if you have one imaginary number as a solution, its conjugate pair would automatically become a solution to the polynomial. So now we want to get into other rules to help us solve these equations. So the next rule we are looking at is the Descartes' rule of signs. And again, you should have seen that in the video lecture, but basically here the idea is you can actually try to see how many positive, negative, and imaginary solutions your polynomial can have. So basically with Descartes' rule of signs, the idea is you have to take the original polynomial, so you can see the original p of x polynomial here, and you have to see how many times the sign on your coefficients is changing. So if you can see here, we're going from a positive to a negative, so our sign changes because you went from a positive to a negative. Going from negative to negative, it's the same sign. Going from negative to negative is the same sign. So again, if we go from negative to positive, your sign changed on the coefficient. You're going from positive to negative. So you can see in the original polynomial, as you just go down the terms, your sign changes 3 times. So that actually tells you that you can end up with a maximum of 3 positive solutions for this polynomial. Then your next step when you're working with Descartes' rule is you actually take the original polynomial and replace your x with negative x. And once you replace it with negative x, simplify your polynomial. And then again, you're looking for how many times does the sign change on the coefficient. So you can see we're going from negative to negative. So that's the same sign. Negative to positive, our sign is changing. We're going from positive to negative. So again, your sign changes. And then you're just going from negatives to negative. So 2 changes here, which means you can have a maximum of 2 negative solutions. And as you can see, this is a 5th degree polynomial. So you can see 3 plus 2 will add up to 5. But here's also something else we have to keep in mind. So they're talking about here in Descartes' rule, the number of positive real roots is either equal to the number of variations of signs. So we know we got 3 variations, so that's that equal to 3 positive answers, or less than by an even number. So if you reduce 3 by an even number, remember your first even number is 2, so just keep reducing these answers by 2. So you can technically have 3 positive solutions for this polynomial, or 3 minus 2 will just give us 1. You can have 1 positive solution for this polynomial. Same thing actually happens with the negatives also. So they're saying the number of negative real roots of the equation is either equal to the number of variations of the sign, when you plug in the negative x. So that's of course 2 negatives that we got over here because we had 2 variations in our signs. And same thing over here, this will also say or less than by an even number. So if I subtract 2 minus 2, I will get 0. So technically that means I can also have 0 negative solutions. So it's actually really interesting the way this Descartes' rule works, because again, remember, it cannot give you a definite answer because we honestly don't know until we start solving the polynomial, what kind of solutions we will have. So this is again laying out options for us. So basically it's saying you can have 3 positive solutions, you can have 2 negative solutions, And since that adds up to 5, that means we will have 0 imaginary solutions. Because remember, whatever is the highest degree, only those many roots I can have. But since we also have these other options, you can actually say you can have 3 positives, no negative, and since this has to add up to 5, that means it actually opens up room for 2 imaginary solutions. So you can have 3 positive, 2 negatives. You can have 3 positives, 2 imaginary, or if you only have 1 positive, so that can be 1 positive, 2 negative, which adds up to 3, which means you would have room for 2 imaginary solutions. Or you can have 1 positive, no negative, and that of course means it opens up room for 4 imaginary solutions. So again, you can, like I was saying, it gives you options, but again, we don't know till we start solving these, which one of these possibilities is it going to be. So it's kind of like we did with the rational zero theorem, where you get a list of all those whole numbers or fractions with the plus or minus sign. And then we basically had to see which one of those would give us a 0 remainder if we did synthetic division. So this is kind of along that same line. They're giving us the possibilities, but then once we start solving it, we will get a better idea of how many positive solutions, how many negative solutions, and how many imaginary solutions we are going to have. So that's actually the next type of example that I want to look at here. But the thing is, when you actually combine a bunch of these different rules together, it actually helps you narrow down what type of solutions you will have. Okay, so you can see this example right here. They're asking us to use Descartes' rule of signs to discuss the possibilities. As you can see, we're only trying to find what the different possibilities are, so we're not really trying to solve the equation at this point. So if you think of this as being our original polynomial, now you can think of this as being our p of x. So if you look at this, you are going from positive x to the third to positive 9x squared to positive 8x to positive 3, right? So since all your terms are positive, we're not seeing a change in our signs. So since you're not seeing any variations in our signs, that actually tells us we will have 0 positive solutions. And that's actually a good thing, getting a 0, because it makes our life a lot simpler. And if you actually look at this statement right down here, we're talking about with Descartes' rule of signs is especially helpful when your number of variations is 0 or 1. And the reason we prefer that is because you cannot decrease it by an even number, right? We cannot do 0 minus 2 and get negative 2 solutions, because that's not possible. You can have 0 solutions, your polynomial can have 1 solution, or it can have 2 solutions or 3 solutions. So 0 and 1 is definitely a good sign because it reduces the number of possibilities. So since there were no variations in signs, we do not have any positive solutions for this polynomial. Now to see how many negative solutions we will have, we will need to take our polynomial and replace all the x values with negative x. So that will give us negative x to the third power for that first term, plus 9, negative x to the second power, plus 8 times negative x, and then plus 3. So everywhere that you see x in the original function, replace it with negative x. So we know if you have a negative number to an odd power, the negative sign will stay. So you will have negative x to the third on that first one. When you have a negative number to an even power, it becomes positive. So the 9x squared will actually stay positive. 8 times negative x will of course end up becoming negative. So you will have negative 8x. And then of course, plus 3 will stay as it is. So now you will notice that we are seeing some variations in our signs because I am going from a negative to a positive. So that's one variation. Then we are going from a positive to a negative. So that's the second variation in our sign. And then you are going from negative to a positive. So again, that's a third variation. So since we have three variations over here, and basically remember when we're talking about variations is that your sign changes from one term to the next. So this will actually mean that we will have up to 3 negative answers, but remember you have to reduce that down by an even number. So 3 minus 2 will be 1 negative. So you will have 0 positives, 3 negatives, and since this is a third degree polynomial, you know you only need a maximum of 3 roots. So that means you actually will have no imaginary solutions. That's going to be one of the possibilities. Or we still have 0 positive. Instead of 3, remember you can also have 1 negative solution. So if you have only 1 negative solution, that means it opens up room for 2 imaginary, because again, it has to add up to a total of 3 solutions. And I think those are about the 2 options that we will have. So 3 negatives, no positive, no imaginary. So you can see that will be this option over here for the 3 negative real roots. Our other option was 1 negative and 2 imaginary. So 1 negative and 2 imaginary is going to be part A. So you have to select all those possibilities as your answer. So it's not just one of them. It's going to be, you know, multiple answers based on how many different combinations you were able to come up with. Hold on a second. Okay, questions on this one, guys? Okay. Okay, let me see what you can come up with as your possibilities for your roots with this example over here. So you've got 3x to the fourth minus 7x squared minus 6 as your original polynomial. So remember, for the positives, you keep the polynomial as it is and just see how many variations in signs you have. For the negative, you will be replacing all the x with negative x. Simplify that and then check and see how many variations in signs do you have, and that'll tell you how many negative solutions we should have. So do we have the answers?
Yes.
Okay, what did we come up with?
I got D, one positive and one negative,
That's it?
I think.
Let's have a look here. You're going from positive to negative, so that's a variation. Then you're going from negative to negative, so that does not change. So that means you have one positive solution, okay? So that part looks good. Then for the negative, you replace your x with negative x. Okay, Mikhail, you're saying wouldn't there be two imaginary solutions? Let's check that. So this will be negative x to the fourth power minus 7. Again, replace x with negative x to the second power minus 6. So again, since both your exponents are actually 4 and 2, which are even numbers, so these will actually just stay as positive. So this will become positive 3x to the fourth, negative x squared to the second power also becomes positive. So that negative 7 does not change. It stays at negative 7x squared minus 6. So even at this point, when you talk about variation, there's only one variation happening over here from positive to negative. So that means, again, we will have only one negative solution. And then, Brandy, you said part D, but you can see this is a fourth degree polynomial. So these guys are adding up to only 2 roots, right? When you do one positive, one negative.
Yeah, so it's A.
So that's why what Mikhail said in chat was correct, because you will have one positive, one negative, but that automatically opens up room for 2 imaginary. So actually we are looking at, what's that, option A? Yeah. Alrighty. Did anybody have questions on this? Anyone who was not able to come up with an answer? Okay. So let's check that. There we go. Okay, so remember I was telling you we need to do basically a combination of all these different rules. So before we get into that, let's take a look here. So you've got a couple different examples to help you out with it in your homework. Now let's get into this theorem on bounds. And theorem on bounds actually ties really well with our rational zero theorem, which is what we saw at the end of the last section, because it actually tells you what the lowest and the highest values should be on our solution. So if you have anything in your rational zero theorem, any numbers which fall outside of those bounds, you can basically discard them. So this actually helps you narrow down some of those options. And the way the theorem on bounds actually works is you have to figure out what number, and we're just calling it a number C. So for the upper bound, we have to basically find out a positive number C, such that when we do synthetic division with this number C, the bottom row is going to be all non-negative numbers, which means you can have a 0 in the bottom row or a positive number. So you basically start dividing by positive 1, positive 2, positive 3, positive 4, you keep going till your synthetic division, the bottom row will be either 0 or positive numbers, so basically non-negative numbers. And that number will become the upper bound for our roots. So basically we're saying there will be no answer beyond this upper bound. Same way, we are trying to find another number C, which will become the lower bound for our polynomial. And in this case, it's going to be a negative number. And the way we know the number is going to work is when your bottom row is actually alternate in sign, which means it should go from positive to negative, or it can go from negative to positive, negative to positive. And you will actually see with this rule on theorem on bounds, we are saying if a 0 appears in the bottom row of your synthetic division, you can actually assign it a positive or a negative sign, if it's going to help you in alternating the signs. So you can kind of use this idea of assigning a positive or a negative, especially for that finding of the lower bound, if you need your signs to alternate. So this will be another thing that will help us narrow down our options. So let's take a look at how we can find this theorem on bounds. So you've got another example for the rule on Descartes. Now let's take a look at this example here for our theorem on bounds. So you can see we are given the polynomial fx to the third minus 17x squared plus 421. So the first thing you should notice is we do have a term missing over here because you're going from the third power to the second power, and we don't have the first power term, so we'll need to make a room for it. So let's start with finding our upper bound. So you can start dividing by 1. So our coefficient is 5, negative 17, 0 for that missing term, and then 421. And remember, we are not looking for a 0 remainder or anything like that. What you are looking for the upper bound is to get non-negative answers in the bottom row of the synthetic division. So of course, remember, you bring the 5 down as it is. We do not change anything on that. 5 times 1 will be 5. You add that with negative 17, which will of course end up giving us negative 12. And you know what? I actually wouldn't go any further than that, because you are supposed to have non-negatives in your bottom row. So the moment you hit a negative, this number is not going to work. So you can actually just leave it there and move on to the next number. So again, 5, negative 17, 0, 421. So again, bring down the 5 as it is. 5 times 2 is 10. And again, you can see that's going to give us negative 7 over here. So this guy is not going to work either. So with number 3, will that work? Because 5 times 3 is only 15, right? And 15 will also end up giving you negative 2. So none of these numbers are working. Let's take a look at 4. That will be 5 times 4, which is 20. So that's good. It's a number larger than 17. So negative 17, positive 20 will give us 3. 3 times 4 is 12. 0 plus 12 will be 12. Of course, 4 times 12 is 48. And again, you can see we're not going to get any negative answers here. So this will become 9, 6, 469. So all non-negatives in here, which means our upper bound is going to be number 4. Okay, so that's actually the number we are going to put here on this side. Now, in that same manner, we have to find the lower bound for our polynomial over here. So for the lower bound, you do the same thing, but now we are dividing by negative numbers, and you're looking for alternating signs in the bottom row. So again, we will start with -1, then we've got 5, -17, 0, 421. So bring down the 5. That's -5. So what will that be? -22. So far, so good. We are looking at alternating signs. Negative times negative will become +22. So that's +22 down here. And our signs are still alternating. 22 times -1 is -22. But of course, you will see this guy will come out to be 399, which is positive. So it's not alternating signs in that last two numbers. So obviously, we know that's where this guy is going to fail. So that's not going to work. So let's move on to -2. It's the same thing. Look for alternating signs. And do you think this guy will work? Because what's going to happen for that last number to give you a negative sign if we want alternating signs? It's got to be a number larger than 421, right? And it's got to be a negative number for us to get a negative sign. So we may actually have to do this. I'm not sure how many times, but it may take us a few tries before we are able to get to that. Because this guy is again just giving us -108. And so, obviously we're not going to be getting a negative sign here either. And so, of course, that means, we keep trying till we hit that negative number, which will work in our favor. So keep trying and let me see what numbers you guys come up with where you are getting that lower bound at. So what do we get, guys?
I got 4 as my lower bound.
+4, -4?
-4.
-4, okay. Is this guy here, when you multiply 148 with -4, you get -592. And this is what I was talking about. So now when you add the +421 with -592, you should see -171. And you can see our signs are alternating because we have +5, -37, +148, 177. So bottom row has alternating signs. So that of course means this guy becomes our lower bound. And you know, it's not always going to be that the positive number 4 becomes your upper bound and negative number 4 becomes your lower bound. It's going to be different for each example. Okay, so let's check this. So yes, this process can get a little tedious. I have seen examples where you almost had to go to 7 or 8 on the positive or negative side to come to, you know, a lower bound or an upper bound. So it can take a little bit of a process, but you know, once you start recognizing that there's a little bit of a pattern, this can actually work a little bit faster. So, you know, again, practice with these, see what you can come up with. So obviously, same thing's going to happen over here with number 11. Now, the last part that we actually have here is putting all of these techniques together. So you will actually see in this example, they're telling us to use the rational zero theorem, to use Descartes' rule of signs, to use the theorem on bounds, and putting it all together to help us find what the real and imaginary roots for this polynomial is going to be. So remember, with the rational zero theorem, we take the factors of our constant term, which become the p values, and then we take the constant from our leading coefficient, which in this case is number 1, and that will become our q values. So q will just be number 1, but for p, how are we going to break 65 down? Other than the obvious 1 and 65.
5 and 13.
5 and 13. Oops. And of course, since those are both prime numbers, we cannot break this down anymore, right? 5 will not be broken down, 13 will not be broken down. So this is kind of nice that we don't have too many options that we have to worry about. So 4 numbers from 65, and then since q was 1, we just had 1. So remember, this is where we do p divided by q. And since we would be dividing everything by 1, you will have 4 numbers, but then with the plus or minus sign, remember, you will end up getting double the options. So from the rational zero theorem, we are getting plus or minus 1, plus or minus 5, plus or minus 13, and plus or minus 65. So we're going to leave these as it is for now. Then let's do our Descartes. And you should actually recognize the name Descartes because it's the same mathematician who came up with our rectangular coordinate system for graphing, René Descartes. It's the same mathematician. Okay, so remember, for the Descartes' rule, we have to look at how many times our sign changes. So for the original polynomial, we're going from positive to negative. That's one variation. Then we go from negative to negative, so it's the same sign. And we go from negative to positive. So those are 2 variations. Remember, 2 variations tell us we can have 2 positive solutions, or you can decrease it by an even number. So 2 minus 2 will basically give us 0 positive. So this equation will either have 2 positive solutions or no positive solutions. For the negatives, remember, you take your polynomial and replace it with negative x. So that will become negative x to the 3rd power minus 9, negative x to the 2nd power minus 57 times negative x, and then plus 65. So when you clean this up, again, negative to an odd exponent will stay negative, so that's negative x to the 3rd. Negative 9 will stay as it is because negative x to the second power just becomes positive x squared. Negative 57 multiplied with negative x, so negative times negative will become positive 57x, and then positive 65 at the end. Okay, so now you will see we are going from negative to negative, so no change. Then we go from negative to positive, so that's one variation. And then again, we are going from positive to positive, so no variation. So this guy only has one variation. And again, 1 is a good number. We like 1 because that means we will have exactly one negative solution. So now when you try and put this together, you will see we can have either 2 positives, 1 negative, and since this is a third degree polynomial, that's already adding up to 3, so that means 0 imaginary. However, if we have only, instead of 2, if we have 0 positive solutions, we will definitely have that 1 negative solution. Then obviously that opens up room for 2 imaginary solutions. So this would be our possibilities: 2 positive, 1 negative, or 1 negative, 2 imaginary. So that's coming from our Descartes' rule of signs. The last one is our theorem on bounds. So for theorem on bounds, of course, we have to find what our upper bound and lower bound is going to be. So let's start with the upper bound. And again, make sure there are no terms missing in your polynomial. And then you start dividing by positive 1 till we get to a non-negative bottom row. So let me see what you guys come up with this guy. So your coefficients will be 1, negative 9, negative 57, positive 65. So keep going with the positive numbers till your bottom row is going to be non-negative. So remember, non-negative means 0 or a positive number. So what are you noticing here as you're trying to find that upper bound?
We can pretty much just, like when solving it, we can pretty much just skip to 9 as a starting point because of the negative 9 being after the 1.
Yeah, very nice, because anything which is going to be 1 through 8, even if you did 8 over here, you're going to get negative 1. But if you change this to a 9, you are going to get 9 and then 0 over here. But then what happens when you move to the next stage?
It'd be a 0 and be a negative again.
Yeah, and you're still going to get a negative. So you're actually going to be in a 2-digit number if you're going to try and beat that negative 57. And I have tried 57, and 57 itself did not work either.
I did 66.
Yeah, what did you get?
I got 1, and then 1, 57, and then 57, negative 57 plus 57, 0.
Oh, okay.
And then 0 for 65.
So 66 minus 9 would be 57. But then when you multiply 57 with 66, that'd be a really large number.
Yeah.
Yeah, I think 3762 minus 57. I think, yeah, that is really, really large. Okay, so basically, here's what I would recommend you guys to do. Since we know that 1, 5, and 13 are definitely part of the play, right? It's only a matter of can we actually use 65 or not. You can basically try and see what 65 gives you, because there's no reason to keep trying, especially if you thought you wanted to try all the numbers from 1 through 65. You know, obviously that will be next to impossible. So we can see, because, you know, the idea was, could we eliminate some of these larger numbers? And it looks like we're not really able to eliminate. Let me just try 65 very quickly and see what happens. Let's clear all of these guys out and see what happens if we did positive 65 here. So of course that would give us 65 minus 9, which will be 56. But you can see when we multiply these, this is where we end up in those 3-digit numbers. And the question is, you know, honestly, we cannot say if this is going to be the upper limit, because we haven't tried the number smaller than that to see if any of those would have worked out. So you can imagine this number is going to be even larger if you're multiplying 3,583 with 65. So, you know, this number will also come out to be positive. So that's really not helping us do that. So I would say let's try with the negative numbers and see if we have a better luck. And then with negative numbers, you know, of course, we are looking for alternating signs. So upper bound was not really working out in this case.
For upper bound, I actually got 14.
14.
14, yeah.
Okay, let's check the math for 14. Whoa. Okay, so that would be 5. 5 times 14. Okay, 70, which will give us what, 13? And then 13 times 14, 182. Okay, and then of course that would be a positive number at the end. And 13 was not working, Mikhail? Was 13 giving you a negative answer?
I actually hadn't attempted 13 because I was doing the math and noticed that every time we incremented with the initial number. Well, okay, sorry, hold on. So I did try 13, and for negative 9, it gave me a 4 for that. If I remember correctly, let me just do that again.
Right, and then when you do 13 times 4, it would actually give you 52, which will end up giving you a negative in this part.
Yeah.
Right? So that's how we know 13 actually does not work. So, okay, I'm glad you were able to find your upper bound. So that is actually a good sign, because that means you can actually eliminate positive 65 from your rational zero theorem. And that's the idea with the upper bounds and lower bounds, is if you get a number and we're saying, okay, 14 is the maximum real number on the positive side that you can have, that means positive 65 cannot be used. And that's the same thing we're hoping to get through our lower bound. So again, start with -1 and again, see what kind of pattern do you have, because we are looking for alternating signs this time. So what do we see, guys? The first couple numbers are not going to work because they're not giving you alternating signs.
Your lower bound should be -5.
-5, okay. And nothing before that worked. I know I tried it up to 3, I think. Was -4 not working?
I honestly just skipped to 5.
You skipped to 5, okay. And Arthur, you said -4 did not work?
-4 doesn't work.
Let's see, that would be 1 comes down as it is, -5, which would be what, -14? 14 times 5 gives us 70. And then 70 minus 57 will be 13. And that's a positive 13. So when you multiply positive 13 with -5, we will get -65, which ends up giving us 0. So remember what we said with the bounds, you can put a positive or a negative sign on your 0 if you want to get those alternating signs. So we've got positive, negative, positive, and you can put a negative on 0, and that creates the alternating sign. So yeah, very nice. -5 will be our lower bound, which actually means you can now remove -65 from our rational zero theorem, and actually you can also remove -13. So you will have positive 13 left behind, plus or minus 5, plus or minus 1. So you can see how we were able to get rid of 3 of those numbers out of the 8. We've got 5 numbers to check from, and then we know we should have either 2 positive solutions or 1 negative solution. Now, if you actually checked your lower bound or upper bound all the way, did +1 or -1 give you a 0 remainder?
Positive 1 gave you a 0.
Positive 1 gave you a 0. And then we just checked our lower bound over here, and you can see negative 5 gave us a 0 remainder also, didn't it? So you know negative 5 is actually also going to play a part in our solution over here. So since you already actually have the negative 5 giving you a 0 remainder, you can actually take your quotient over here. And remember how we talked about simplifying it? Or if you have the answer from your, Brandy, I think you said positive 1?
Yes.
Yeah, so you can use that quotient also to help you simplify and see what the other two answers come out to be. But since this is what I have up here on the screen, we will use that. So our quotient is, the original was a 3rd degree polynomial, so this is 2nd degree, x squared minus 14x plus 13, and now you can factor this. So what do you think this guy will factor into?
I use the quadratic formula.
Oh, you use quadratic formula? Are we not able to factor this in? What did you come up with your answers, Brandy?
My answer, I got negative 5, 1, and 13.
Negative 5, 1, 13. Okay. Yeah, because if you actually look at this quadratic polynomial over here, you're basically trying to find two numbers that multiply to give you 13 and add up to give you negative 14. So of course 13 would be 13 times 1. If you make both of them a negative sign, negative times negative is positive, so that gives us positive 13. When I add negative 13 with negative 1, it gives me negative 14. So this guy factors into negative 13 and negative 1. And then when you take each one of these and set it equal to 0, you should have the same answer that, Brandy, you got from your quadratic formula. So you should get x equals positive 13 or x equals positive 1. And then don't forget, we also had x equals negative 5, when we did our calculation for the lower bound. So positive 13, positive 1, negative 5. So you will see we actually ended up with this combination over here, where you have two positives and one negative solution. And then you can see the positive 13 was what we had left over from here. We had negative 5 from here and positive 1 from here. Yeah, now, it's not always going to work out in this way, because sometimes out of this whole list of rational zeros, you may only get one of them to work. Because remember how we had seen some solutions could be irrationals, like negative 2 plus or minus square root of 5. So you can sometimes come up with those answers. Of course, we can come up with imaginary solutions also. So this is actually a little bit of in a way, a simpler example, because all of the answers we came up with were, part of our rational zeros. But like I said, that's not always going to be the case. All right, so let's go ahead, plug these answers in. So we've got negative 5, positive 1, and positive 13. Okay, questions on this one, guys? Alrighty. And your next example is actually going to be similar to this one, where they will again ask you to use the rational zeros, the Descartes' rule, and theorem on bound. So I'll let you guys attempt that on your own. And as always, if you need my help, definitely let me know. So those were the options, like I said, to kind of narrow down our search for those rational zeros by putting all of these theorems that we have learned, together. Now, when we're actually getting into section 3.4, we're actually now getting into the graphing of these polynomial functions. So we've done the solutions and, solving in the previous sections. Now we're getting into graphing. So, of course, when we're talking about graphing, polynomial functions that are degree 0 or degree 1, those end up giving us a straight line. So, when we're talking about degree 0, you're actually talking about a horizontal line, because they can be, y equals 3, which will be a horizontal line. This is degree 0, when we talk about degree 1, that can be y equals x plus 3, because your x is raised to the first degree. Again, it's going to be a straight line. When we're talking about a second degree polynomial, those are, of course, are parabolas, because your second degree would, of course, be of the form y equals x squared. So, of course, we're getting into graphs in this section, basically to see what happens if they are a degree higher than degree 2. So greater than a degree 2. So the one thing that we actually talk about when we want to draw good graphs is we are going to talk about what kind of symmetry the graphs will have. And we've already discussed symmetry in chapter 2. We will also talk about the behavior of our graph at the x-intercepts. And by behavior, we mean, is your graph actually going to cross the x-axis? So will we actually have, the graph crossing through that line for the x-axis, or is it going to be, like a parabola where it will come, touch the point, but basically go back, go back up instead of actually crossing the line? So that kind of affects the shape of the graph. And then we will actually also talk about the leading coefficient, how that affects the shape of the graph, because your leading coefficient will actually tell you if both the arms of your graph should go up or should both the arms go down, or basically one arm goes up and the other one goes down, and depending on, which side will go up and which will go down. So all of that comes from your leading coefficient of your polynomial. The other thing kind of that helps with, graphs of functions that we can't really imagine what the shapes will end up looking like, because, we've never really seen, or we don't often see these graphs, is this idea of the intermediate value theorem really comes in handy. So basically, the intermediate value theorem says that a polynomial function takes on every value between two of its values. What that really means is if you have, 2 points on your graph, the idea is if it's going to take on every value, that means you will actually have a continuous curve on your function. It could be, something like this. It could be just a straight line, but the idea is you should have a continuous curve. If you remember when we had talked about the piecewise functions, how some of those functions were jumping. So, it would stop here, but then start here and go and continue on its way. So we're saying that's not going to happen here. You're not going to see a jump. So if you go from one point to the other, you should basically be able to do a continuous shape from one point to the other. And that really comes in handy when we're looking at these graphs. So basically just a revision on your symmetry. Remember, if you have an even function, then your graph is symmetric about the y-axis. And that basically means if you plug in a negative value, a negative x for your original x function, you should come back to the original. In that same way, if we plug in a negative x in our function, it should basically make our whole function a negative. And this only happens when we have an odd function, and odd functions have symmetry about the origin. So remember, O goes with O. The third symmetry, and we talked about this but separately in chapter 2, was that quadratic functions bring their own symmetry. Remember, they have their axis of symmetry, and the axis of symmetry is always at x equals negative b over 2a. So even functions, symmetry about the y-axis; odd functions, symmetry about the origin; and then quadratic functions have their own axis of symmetry, and that will be the equation x equals negative b over 2a. So let's take a look at that. Okay, so let's take a look at this. Okay, so they're again talking about what kind of symmetry this function will have. Now, if you remember, when we had talked about symmetry in chapter 2, we had talked about looking at the exponents for your variables. So you can see you have 2x squared, so that's an even number. Then you have 36x, which is an odd number because that, of course, has an exponent of 1. And then 9 actually technically is x to the 0 exponent. So you can see this is actually a combination of even and odd exponents. So technically, this function is what we would say is neither, because it's neither even nor odd. But this is a second degree polynomial. So this is actually taking us into that third type of symmetry where a quadratic function has its own symmetry. So that's actually what we will need to do over here. So since this is a quadratic function, it will have its own symmetry. And remember, the axis of symmetry is at negative b over 2a. So can you tell me what that number comes out to be when you solve for negative b over 2a?
Negative 18.
-9.
Yeah, that's what I was thinking. Brandy, looks like you left a 2 out somewhere because our b term is going to be 36 from that middle term, right? And
Yeah, I
then
forgot the A.
you forgot the a, okay. And then, yeah, your a is 2. So you're basically taking negative 36 dividing by 4, which will give you 9. So your equation is x equals -9, and looks like that's the only option we have here. So be careful because in chapter 2, we had only talked about symmetry with respect to origin or the y-axis, but now for this chapter, we need to remember that quadratic functions have their own symmetry. Alrighty, very nice. So let's check this answer. Okay, what kind of function is this and what kind of symmetry will it have? Is this an even function, an odd function, a quadratic function? So look at the degree on your...
Isn't it an odd function?
Yeah, very nice, because you do have 7x to the third power, so we know that is an odd number. The x by itself, of course, has an exponent of 1. That is also an odd number, so this is going to be an odd function. And odd functions have what kind of symmetry?
Symmetry about the origin.
Very nice, yeah, O goes with O, so symmetry about the origin. So that means we're, of course, looking at option C over here. One thing I did want to point out, if you look at option A, they're actually not giving you the answer. They're giving you an answer box. So if this was a second degree polynomial, then of course they would expect you to type the answer in there. So they do kind of keep changing that format on you a little bit. Alrighty, very good. So you should have a couple questions on symmetry over here. So I'll let you guys work on that. Now let's get into the behavior at our x-intercepts. And this is what I was talking about, because if you look at this function over here, on the left-hand side at this x-intercept of -1, 0, you will see it is actually crossing our x-axis. At this x-intercept of 2, 0, you will see our graph will touch the x-axis, but it does not cross. And this actually comes from the factors where these ordered pairs came from. So you can see x plus 1 is what gives us x equals -1. X minus 2 is what gives us the ordered pair, or the x value of 2, right? 2, 0. So you will notice this guy was actually raised to the second power. And when it's raised to an even exponent, that's where it does this behavior of touches but does not cross. When it is raised to an odd power, because you can see x plus 1 is raised to the first power, so that's an odd number. So for odd numbers is where your graph will actually cross the x-axis. And you will see that here in this little theorem for the behavior at x-intercepts. If your root is raised to a multiplicity of k, or if the exponent is a k, and that k happens to be an odd number, then your graph will actually cross the x-axis at that x-intercept. If your multiplicity k is an even number, then the graph will touch, but it does not cross the x-axis at that number. So remember, for k is odd, you can actually remember the behavior of x to the third power, or just remember the behavior of the line y equals x. For when k is even, remember what a parabola does. A parabola touches but does not cross an x to the third function, or like I said, think about the line y equals x, which is a line that goes up like this. So this would be, you know, our y-axis. This could be our x-axis, and you can see it actually crosses our x-axis. So this will be the graph crosses the x-axis. So either one of these. So when k is odd, the graph crosses. When k is even, it touches but does not cross. So let's try and use that in our examples over here. Now, not all examples are going to be this straightforward, where they're already giving it to you in the factored form with the exponent on top, but you know, this is a good gateway example to begin with. Okay, so as you can see here, you have x plus 10 to the third power. So you would of course take that x plus 10, set it equal to 0, which would end up giving you x equals negative 10. So that would be your x-intercept of negative 10, 0. You will take x minus 6, same thing, set it equal to 0, which will give you x equals positive 6, and that becomes your ordered pair 6, 0. Okay, so the first thing you are doing is typing in those x-intercepts as ordered pairs, so negative 10, 0, and positive 6, 0. Okay. Now they want to know where it's going to cross at the x-axis. So you can see this one here was the odd number. So remember, for the odd number, you can think what the line y equals x does. So this actually crosses. So that means this is where our graph is going to cross the x-axis. For the even exponent, remember the parabola. So a parabola touches but does not cross, and that's what's going to happen over here at 6, 0. Your graph touches, but it does not cross the x-axis. So when they're talking about the graph will cross the x-axis at the point, that's of course going to be at that negative 10, 0. And again, you are typing these in as ordered pairs. And then this one is saying the graph will touch but not cross the x-axis at the point 6, 0. Do we see that? Questions on this one? Okay. Let me see. This one again is actually given to you in the factored form. This is kind of what I was hoping for. Okay, so you can see there would be an example like this where it's not given to you in the factored form. So how are you going to factor this? Because, you know, till we don't factor it, we will not know what each factor is raised to, and what kind of behavior it will have.
Would you factor out x squared?
Very nice. Yeah, because that would be common between both our terms. So what does that leave you with?
X minus 6.
Very nice. All righty. Yeah, so go ahead, factor out your polynomial. Then, of course, like we did in the previous example, take each factor, set it equal to 0. So that will tell you what each of those x-intercepts should be. And then looking at the exponents on them, you will know what kind of behavior they will have. And honestly, for this x squared, you can just leave the square out and you get x equals 0. Because that would be the same thing if you took a square root on both sides, and you will still end up getting x equals 0. So what are your two x intercepts over here?
Would it be 0, 0 and 6, 0?
Very nice. Yeah, you would get 0, 0 from this first one. X minus 6, so when you move 6 to the other side, you get x equals positive 6. And that would be 6, 0. Now, which one will have what kind of behavior? So where is your graph going to touch but does not cross, and where is your graph actually going to cross the x-axis at?
It'll touch at 0, 0 and cross at 6, 0.
Very nice, because this is raised to the second exponent, so this will have the behavior of a parabola. So this is where it touches but does not cross. And then, yeah, since this is x minus 6 raised to basically the first power, this is where your graph actually crosses the x-axis. Alrighty, good job. So let's see. 0, 0 and 6, 0. Okay, and then I think they're gonna again ask us the same questions. So it crosses 6, 0. Okay, and touches but does not cross at the origin, which would be 0, 0. And let me actually very quickly show you the graph for this. So this is x to the third minus 6x squared. Yes, I'm leaving this written on script on purpose so you can kind of verify, where it touches and where it crosses. So you can see right here at 0, 0, you can see our graph is touching, but it does not cross the x-axis. But then at the ordered pair 6, 0, which is right over here, your graph is actually crossing the x-axis at. So yeah, it just takes a little, graph to look at and see what kind of shape this will have. Now this is, hard to kind of get it on one screen, but you can kind of see it still has that x to the third shape that this graph has over here. But, of course, by having that negative 6x squared, you can see it's changing the shape just slightly a little bit. So this is talking about the behavior at the x-axis. So we've talked about symmetry. And again, if you actually look at the graph here, you will notice it has no symmetry. And the reason for that is this is not an even or an odd function, because you have the third power on your x and the second power on your x. So you can see This does not have symmetry with the origin or the y-axis. This is not a second degree polynomial either, so it does not bring its own axis of symmetry either. So you can kind of verify that with the graph and see. Now, the next thing we actually want to talk about is the behavior of your arms based on the leading coefficient test. So when we talk about the leading coefficient test, we actually want to know when our leading coefficient term over here, do we have a positive or a negative leading coefficient? And is the degree of our polynomial an odd or an even number? So it literally comes from this first term of your polynomial. So the nth power, we will know whether it's going to be an odd or an even number. And then your a sub n, you will know whether it's going to be a positive or negative number or not. And you know, again, for these leading coefficient tests, you can use these functions here again to help you out with the leading coefficient test as well. So let's take a look at it. We are basically saying, and there's three different ways that I'm actually showing you how you can interpret this leading coefficient test. So here is based on the limits, and you will actually have questions that will ask you to write these limits. And limits is basically, again, we just want to know what happens to your function when your x value is either going towards positive infinity or negative infinity. But these limits also help us with, you know, where the arms of our graph is heading. So we are basically saying if your polynomial is an odd function, so basically a first degree polynomial, third degree polynomial, you know, fifth degree polynomial, any of those odd numbers, but then your leading coefficient is a positive number. So in that case, what happens is when your x is going to positive infinity, your y value or your function is also going to positive infinity. When x is going to negative infinity, your function is also going to negative infinity. And that's actually what's happening over here with this function, because this is an odd degree with a positive 1 as your coefficient. So you can see as my x goes to negative infinity, my y is also going to negative infinity. As my x goes to positive infinity, my y is also going to positive infinity. With changing our coefficient for an odd function to a negative, your direction actually changes. So now when x is going to positive, you will actually see your y is going to negative. When x is going to negative, your y is going to positive. So that actually means if you look at the graph for the function, I'm going to do it here. If you look at the graph for the function negative x to the third, remember by putting that negative, you are creating a reflection on this x to the third function, which means this arm would go up and this arm would go down. So as x is going to positive infinity, your y is going to negative infinity. And on this side, as x is going to negative infinity, your y is actually going up to positive infinity. So that tells us where the shape of our graph is going to go. And you're going to have that same thing with the even function. So when it's even and positive, actually both are, as x is going to positive and negative, your y is always going to positive. When you have an even function with a negative coefficient, x goes to positive, y goes to negative infinity. As x goes to negative infinity, your y also goes to negative infinity. So for this third and fourth case, you can actually think of a parabola. So you can see this is a parabola with an even exponent, positive coefficient. So in this case, as x goes to positive infinity, you can see your y is going up. So y is going to positive infinity on the left-hand side. As x goes to negative infinity, your y is still headed up to positive infinity. If you just create its reflection, you would have y equals negative x squared, and we know that's a parabola that opens downward. So in this case, as x goes to positive, y goes to negative infinity. As x goes to negative infinity, your y is still headed down to negative infinity. So these two functions really help you out with the behavior of the x-intercepts, with the leading coefficient test, and then just by creating their reflections, you can see what the other behavior for that leading coefficient test is going to be. So like I said, you have it in terms of the limit definition. This is a table that I have created. So it shows you when your exponent is odd, but the leading coefficient is positive, what kind of behavior the x and y will do depending on is the x going to positive or negative infinity. Same thing over here with the odd and negative. So you can see what these behaviors are. And then, you know, with even exponents, no matter where your x is going, your y always goes either up or down, because, you know, think of these as your parabolas. And then for these guys, you can think of them as your either the x to the third, or just think of the y equals x function, because they also help you with both of these definitions here. And then I like your textbook is actually showing you, you can see this is basically a parabola that opens up for even exponent with a positive leading coefficient. This is a parabola that opens down. This is for, again, even exponent with a negative coefficient. This function over here, you can almost imagine this being either a line with a positive slope or a line with a negative slope, and that happens with an odd function, positive or negative leading coefficient. So use whichever one of these you think is going to be the most helpful to you, but for our purposes, we are interested in knowing where the arms of our graph is headed. So again, if you look at this graph over here that we just looked at, you can see here as our x is going to positive infinity, which is of course in this direction, you can see our y value is going up to positive infinity. With the left-hand side of our graph, you can see as our x values are going towards negative infinity, our y values are going towards negative infinity. And this happens when our n is an odd number and our leading coefficient is a positive coefficient. So that is exactly what we had over here, odd and positive. Okay, so let's pick some examples from our homework over here so you guys can kind of see how this works out. So this one here you can see is asking you just in terms of as x is going to positive infinity, where is your y headed? So we have, again, only the leading coefficient. You can see we have x squared functions, which means our n is an even number, and you have a positive 10, which means our leading coefficient is a positive number, and that should actually be greater than 0. So an is positive. We have an even function, even leading coefficient. So even and positive, of course, means we are looking at, I need to do that. Even and positive, of course, is going to be this square over here. Even and positive, of course, is going to be this option over here. So you can see when x is positive or x is negative, it doesn't matter. Your y is always going to go up to positive infinity. Of course, you can verify that over here also with the third case scenario. So any one of those is going to help you. But basically the idea is as x goes to positive infinity, y also goes to positive infinity, because just imagine a parabola opening up. X goes to positive, y also goes to positive. So that's all you are typing in here is positive infinity. Yeah, I might have to make this smaller for this to work. There we go. Alrighty. Let me save that so I can check your answer. Okay. So again, so some of these questions will be based on just, what is your y uh, value is going to do when x is going to positive or negative infinity. But I actually wanted to show you the ones with the limit. And pay attention to these as x goes to negative infinity. So they're being very specific in this case. So just make sure you know which direction your x value is going in before you can see where the y goes. So with this function, you can see we have 10x to the third as our leading coefficient. So in this case, you can see our n is an odd number. That's our exponent. And an, which is 10, our leading coefficient, is a positive. So you have an odd exponent with a positive leading coefficient. So again, like I said, you can think of the line y equals x. You can think of the cube function, so x to the third. And x to the third, of course, has this shape. Either one of these is a good guide. So you can see in both of these, as your x value is going to positive infinity, your graph is headed upwards. So y is going to positive infinity. For x going to negative infinity, which will be on this side. So if x is going to negative infinity, you can see your graph is going downwards. So y is also going to negative infinity. And of course, that's the same thing happening here with the cube function. So as x goes to negative infinity, y also goes to negative infinity. Okay. So use that table or that chart, however you want to look at it, to help you through these. So similar examples to that. I was actually hoping to show you the limit. This is what I was talking about. So yeah, you will have some questions which are actually going to give it to you in this limit format, but they're still asking the same thing. You're still using the leading coefficient test over here. So let's pick an example that looks a little different. Let's do this guy here. So what is our n value? Odd or even?
Odd.
Yeah, because it's x to the first power, so n is odd. And your leading coefficient, is it positive or negative?
Negative.
Negative, because you have a negative 6. So basically you can see you have odd and negative. So again, if we come back to our table over here, when it's odd and negative, you are looking at case 2. So that means this is going to be where, again, you're looking at the second one. So when x goes to positive infinity, y goes to negative infinity. And x goes to negative infinity, y goes to positive infinity. So here they are asking us which of these will be correct. Now you can see they're talking about in terms of x going to negative infinity. Remember, this is a graph that would look like this. So when x is going to negative infinity, which is this direction, your y is going up to positive infinity. So of course that means you're choosing the second option to go with this. So it's exactly the same thing. Like I said, the presentation is a little bit different because they are, giving it to you in the limit setup. And the reason I want you guys to be familiar with limits is because if you end up in a higher level math class, then limits is something that they will be talking about more than just with, x goes to positive infinity with the arrows and y goes to positive or negative infinity. So especially if you get in like a calculus course, you will be seeing limits is going to be one of those first things that is going to be brought up. So I want you to be familiar with the notation of this. So you will have a couple examples on, in the limit format. So you should be able to work through that in the same way. Now, the next thing you are actually going to have, and I wanted to show you, is kind of going to be something like this, where they're giving you the graph, and then they're asking you to discuss the symmetry, the behavior, and where your x and y axes are going. So you can kind of look at that. We can make this guy a little bit bigger. So if we had to talk about symmetry, what would you say about the symmetry of this function?
That it has neither.
Yeah, because you don't see symmetry with the origin, with the y-axis, and obviously this is not a parabola, so it does not bring its own axis of symmetry either. So you would basically say it has no symmetry. What would you say about the behavior at the x intercepts? So at which x-intercept does it cross? At which x-intercept it touches but does not cross?
0, 3 it touches, and -1, 0.
So when you're saying 0, 3, you're talking about the point here.
Oh, I'm sorry, 3, 0.
Yeah, be careful. So yeah, 3, 0, of course, you can see is where it touches, does not cross. And then this would be -1, 0 is where it touches. Now, what can you say in terms of the leading coefficient test? As x goes to positive infinity, where is your y going? As x goes to negative infinity, where is your y going?
As x goes to positive, y goes to positive,
Okay,
and
very good.
x goes to negative, y goes to negative.
Yeah, very nice. So basically, those are the kind of things they're asking you to do by visually inspecting your function. But of course, remember, our goal here is to actually find these characteristics so that we can actually draw our own graph. So that was what you will see after these limit questions, I believe. Yeah, so this is the last part. Now, again, since we're not doing these exams by hand, you will not have to graph by hand, but I did want to show you what the basic process is, and that's kind of what we did with that graph example. Start by talking about, symmetry. Look at the function and see what kind of symmetry it will have, because that will again help you kind of eliminate the choices from the different graphs they will give you. If it's straightforward, fine, where all the zeros or basically your x-intercepts are going to be for this function, and then you can determine, what kind of behavior they will have. Look at the leading coefficient test and see what your function should be doing as x goes to positive or negative infinity. And again, since we are not really graphing these, but if we were graphing these by hand, then you always want to try and find, more ordered pairs. If possible, we want to try and find the y-intercept also, so they can give us a better idea of what the shape of the graph will look like. And then, ultimately we try to draw our graph based on that. So looking at this example over here, let's see if we can keep those 4 graphs in our window here. Okay, so your given function is, and again, you can see it's in the factored form, x minus 4 squared and x plus 1. So, of course, you should see this is a 3rd degree polynomial because you've got x squared and x coming out of those 2 factors. So this is a 3rd degree polynomial, which actually tells us, does it tell us anything about the symmetry? Are you able to see anything about the symmetry from this?
There is no symmetry.
Yeah, the only way you would be able to calculate symmetry here is either by replacing your x with negative x to try and see if it's an odd function or an even function. The other way would be to expand out your factors, so multiply everything together and see what your exponents will end up looking like on the x variables. So at this point, you can also see the 4 graphs, and it really does not look like any of these have any kind of symmetry. So I think it would be safe to say this guy has no symmetry. Now, when we talk about the behavior at the x-intercepts, can you tell me what kind of behavior we should expect? So your 2 x-intercepts would be coming from these 2 factors. So what kind of behavior should we see at that first one, and what kind of behavior we should see at the second one?
You should see a touch with the first one, and that'll be at 4, 0. And then you'll see a cross with the second one at -1, 0.
Very nice. Yeah, because this is with an even exponent, so it touches but does not cross. And then the x plus 1 was at an odd exponent, so it will actually cross. Very nice. So we have our behaviors, and you can kind of see, and I'm not sure how visible this is for you, but you should see with graph B and C at +4, we are noticing that touch, and at -1 we have the cross. And then in graph B also at +4, you should be able to see the touch, and at -1 the cross. Let me make these guys bigger. So this is graph B over here, and then this is graph C. So you can see these are the only 2 that are satisfying that behavior. If you look at graph D, you will actually see this is at -4, where it's touching and does not cross, and +1, where it's touching and does not cross. And you can see they are trying to confuse you, because inside the parentheses you had x minus 4 and x plus 1, and that's the same thing happening here in graph A. So just by that behavior, you can see we are able to eliminate graphs A and D. Now let's talk about the leading coefficient test. So you can see this is a positive x to the second power, so you will get x squared from here. This is a positive x from here, so when you multiply that, you get x to the third. So this is of course telling us our n is an odd power, and our leading coefficient is a positive number. So what kind of behavior do you expect from the arms of this function, from the leading coefficient test?
As y goes to infinity, x goes to infinity, and y goes to -infinity, x goes to -infinity.
Alrighty, so when it's odd and positive leading coefficient, remember you can just use the line y equals x. So in this case, as Brandy mentioned, as x is going to positive infinity, which is this direction, your y is also going to positive infinity. As x is going to negative infinity, your y is going down, so y is also going to negative infinity. And so if we talk about this general shape, is it going to be graph B or C which will satisfy our function?
C.
Yeah, it's going to be graph C, because this is where, and let's make that guy bigger. You can see this is where this arm of our graph is going up as x goes to positive and y goes to positive. This arm of our graph on the left is of course going left and going down. So x goes to negative infinity as y goes to negative infinity. So yeah, very nice. It is going to be graph C, which will satisfy our polynomial over here. Okay. So use those techniques to help you out with these examples over here. So you should see a bunch of different examples on that. You know what? Let's do this. This is a 4th degree polynomial over here. Let's see if we can again get all 4 of them. Okay, so what do you think about symmetry with this guy? Negative 2 x to the 4th plus 4. Go ahead.
I would say even.
Yeah, it's an even function because you have x to the 4th power and the constant number 4. Remember I was telling you how you can think of this as being x to the 0 power, which in this case we pretend that 0 is an even number. So this will be an even function. Since it's an even function, it will have, where do even functions have their symmetry?
Y-axis.
Very nice. Symmetry about the y-axis. Alrighty, very good. What kind of behavior do we expect at the x-intercepts? What will those x-intercepts be? How would we find those x-intercepts? Okay, I'm gonna pick up this example. I actually just noticed the time for our Math 121 class. So we will pick up with this example next time. I want you guys to think about how you are going to come up with the x-intercept, because you can see from all of the graphs that you do actually have an x-intercept, or 2 actually in this case. So you need to figure out how you will calculate those. So kind of keep that in mind as we are picking up this for the next class. So since it's about 11:04, I will give you guys a 5-minute break. So at about 11:09, let's come back for our lab class, okay? Alrighty guys, I'll see you in a little bit.